All right, I will begin with a word of prayer. Close this actually before I dump it on everything. Is there a cap? Oh, there it is. So, dear Heavenly Father, we thank you for this day. Thank you for these students. For you to just give us insight to cover a little bit about supermanifolds. Taylor, in your name I pray. Amen. All right, so I will try to briefly explain to you what is meant when we talk about a function being super differentiable. I mean, that is the fundamental sort of notion behind everything here. So here it is. Basically, we have some space which you could, well, I guess I have, trying to decide whether I want to do it. I guess I'll keep it real in here. Let's say RPQ. And this is a, this is a set of, you have these commuting and anti-commuting variables, right? So you could think of those as literally variables. I mean, they take their values in supernumbers that are built from either an even number or an odd number of Grassmann generators. And again, this RPQ is actually, for us, this is built what? As I described, it's built over the Grassmann, the Grassmann algebra with the complex coefficients. It's the so-called the real subset of that. So it's like Z in the sky, such that Z star is equal to Z, as I explained in some depth last time. So you're using complex coefficients, but really the coefficients even at the Grassmann level are real. They're either real or they're pure imaginary, okay? All right, anyway. So, definition. Let U be open. Ooh, I really shouldn't have used Coke on this, it's sticky now. In RPQ, and so what that would mean, oh man, it's really not working. I'll be right back. Yeah, this is the time of the semester that all the board cleaner has run out and we have not resupplied it to the department. It happens every single semester.
Like the only professor I've seen that actually uses the board cleaner in the math department, though.
Oh yeah?
Yeah.
Why is that?
Dr. Sprada uses his hand and Dr. Lang
Just
kind of lets it soak.
he just kind of lets it be. Yeah. I guess that's their prerogative. But I like a clean board. Otherwise it drives me nuts. Sorry for this very exciting interlude. What I'm trying to describe here, what does it mean for the set to be open? That's open like in the sense of a norm space, right? So that means every point's interior where you're using the basic open sets are exactly just those that are furnished from the norm. Remember the norm was just like the sum of the moduli of the components of the Grassmann. So it's like, if you looked at it from another perspective, you might call this L1 or something. It's a set of L1 summable sequences in some sense with an extra algebraic structure. L1 summable means, we have an infinite series of coefficients, right? And that infinite series converges. That's by our assumption of the construction of the supernumbers. So that's there, and that's also how we're defining open and such. But anyway, that level of detail doesn't matter that much here. U open in RPQ, and let's look at a function from U to say the supernumbers, which I guess I would just say, I'll just call them lambda. So this lambda would be something like, I guess it would be in our current notation like C sub C, direct sum C sub A, or something like that. You could replace that with other things like, I mean, you could make it, you could also put this in place, you could replace this with just the, these things, right? Like you could replace it with the commuting plus the anti-commuting supernumbers for a range if you wanted. We'll think more about that as we write this definition, whether or not it matters. Okay. So now the definition I'm about to write, I think, is equivalent to the one Alice Rogers gave originally, but I think maybe we first found it in Yedick and Pilch. Actually, no, this definition is straight from Alice Rogers' paper. Oh man, I don't have which one it was right off the top. Okay, here it is. Number one. Good grief, do I have any marker here that's not trash? Sorry. Everything I pick up doesn't write to the board.
I'm gonna go on. Oh, dark.
I mean, I've got oodles of them. I don't think things, but I just have to keep trying. And I should probably throw out the ones that don't quite work. Anyway, one, F is G naught on U if F is continuous in the usual sense of continuous function on a norm space. All right. 2, F is G1 on U, or you could say super differentiable on U, if there exist P plus Q continuous functions, GM F that are mappings from U to lambda. Let's just use lambda, and let's just call this whole thing lambda, with the understanding that lambda is some set of supernumbers. Okay. And in here M is equal to 1 to P plus Q. These are continuous functions, and also another function, eta. There's no danger of confusion between this and the Grassmann generators, so don't worry. That goes from RPQ to lambda, such that what? If A comma B and A plus H comma B plus K is an element of U, then you have the following: F of A plus H comma B plus K is equal to, I'll get out of the way, F of A comma B plus, and then I'm going to break up these next terms into two different kinds. The sum M equals 1 to P of G lower M F oh, curses. It matters here what side of things you write things on. In general, I have to be careful. I gotta put the H first here. HM GM AB, GMF, A comma B plus the sum Q equals 1 to P, Q, listen to me, sum alpha equals 1 to Q of K alpha, G alpha F, A comma B, right? And then there's one more thing. What do you think? So I said there exist these functions, these g's, right? If you look at this, Jess, if you can see what's going on, right? If I subtract this to the other side, it gives you the change in f between a plus h, b plus k, and ab. So I'm saying it's equal to this stuff, all right? Then plus another term. And this isn't quite the way we package things in advance, but it's kind of similar.
Frichet.
It's, yeah, this is like a Frichet derivative, but where it's written a little bit differently. The next term here is the error term, let's say. What you do is you have the length of h comma k times eta of h comma k. And that's inequality. So it's we characterize superdifferentiability not directly, at least in Alice Rogers' definition here. There is a corresponding limit thing you could write, but this is actually just an explicit, computational statement as well. I mean, it's another way of attacking the Frichet derivative, actually. But there's a little bit more fine print. Where what? What do you get about this eta term? The norm of eta, h comma k, goes to 0 as what?
H comma k goes to a comma b.
Actually goes to 0.
Oh.
So that going to 0,
right.
yeah, the way it's
Yeah.
in a different formalism, it might do that. Yeah, sure. We say f is super differentiable in this case. Or you could say, more succinctly, you could say f is an element of G1U. And I guess to be more descriptive, I could add a lambda here because we're talking about lambda valued.
So you said that term over there, like the kind of the mock Frichet, the error. You said it's an inequality, an equality or inequality, or
Equality.
Is that,
This is equality. Yeah.
well, what? How does that term come out of there? Arise?
Well, if you solve this, right? So let's see here.
Eta h k.
Yeah, what happens if we solve what we just have here? Let's just I gotta go to Walmart and buy some board cleaner.
So it's just solved within this formula. The rest of the terms.
Okay, so if we solve, so we'd have what? We'd have f of a plus h, b plus k, minus f of ab, minus, I'm going to use a m equals 1 to p plus q notation just to get it done with. GM f, oops, h, whatever, right, hm, gm, f, right, a comma b. Then all of that divided by, right?
Yeah, the norm of eta of kh. Or hk.
Right? This is all equal to
Eta hk.
eta hk. provided that we're close to 0, 0, but we're not there.
Yeah.
We can make this division. And this condition that eta, and of course the norm, I mean, you also know that the norm of, this is still true in this larger context, because the norm is still the norm. The things you can prove about norms still continue to be true for the supernorm, even though it's an infinite dimensional context. A lot of the things you proved in finite dimensions also carry through. One of those things being that if the norm of something goes to 0, then it's also true that that thing goes to 0. So this superdifferentiability implies that that quotient in fact goes to 0. And you're right, that is the Fauché quotient. So like, definition, if you have, f from u to lambda, right? And then f is Fauché differentiable. What's that mean? At z, an element of u, if there exists a continuous k-linear function I think here we would say r-linear, because I'm working in the real context. Okay. My thesis is set up for either r or c, making sense here, but to use r-linear function, I would usually use the notation d sub z, f, mapping from rpq to lambda, such that what? The limit. I use capital H as a notation for the pair h comma k. Yeah. So you got yourself f of z plus capital H. Right, now this looks exactly like what I wrote in advanced calculus, right? I mean, that's one of the beautiful things about the Fauché derivative is not only does it sort of generalize all of your different favorite real derivatives, it also extends to infinite dimensional norm space context just the same. It gives us a notion of differentiability there, which is in tune with our ordinary. But you see, so I just want to draw your attention. What is the difference between Fauché derivative? Like, what is the difference between Fauché differentiability and superdifferentiability then?
I mean, for that we don't assume anything about like linearity, do we? Except
Not directly, right? That's true. I mean, I think that's the heart of the matter. But it's, I mean, I agree with you, but I sort of profoundly disagree with you.
okay.
I mean, I agree with you, but at the same time, I want to say not only is this linear, it's in fact superlinear. Let me show you the difference. So here, we've assumed R linear, DZF, right? If you really boil this down, this right here, in the definition of superdifferentiability, is exactly the DZF acting on H, right? So in other words, another way you could characterize superdifferentiability is superdifferentiable means what? It means that you can write the Fauché derivative in terms of this. This is kind of an ugly coordinate-based version of this definition. You could be a little bit more abstract about all this. I mean, what this is right here is essentially saying, I mean, you can think of it this way: the Jacobian matrix has a very special form. But don't get too carried away with that. How big is the Jacobian matrix of the differential here?
Infinite.
Yeah, it's infinite. But I do have this kind of finite expression here. I mean, this is from 1 to p plus q. P plus q are numbers. But this is a very special formula because it's, you see what it has here is, man. Sorry, it's been a while since I've been into this stuff, and the thing that I want to say that the Fauché derivative is right linear, but I'm seeing a left linearity here from this expression. I almost wonder if I should put these on the other side. I mean, there's two different ways you could go here, right? You could define superdifferentiability like this, or you could in principle also define it like let's say G. The difference, and you're like, isn't that just the same thing? I mean, all you did was change the side that's on, right? I put the coefficients over here versus over here. So algebraically, what the difference would be is if you look at dzf, right? And you multiply it by a commuting superscale. Oh, that's it. It's the commuting super. I'm sorry. It's coming back to me now. So if I take, say, h. Oh, I'm sorry. What I'm thinking about doesn't. Sorry, it's. Let me just. I'm trying to think about two things at once. Let me pick one and talk about it. Suppose you have. Oh no, I shouldn't do that, right? I shouldn't do that. The domain of dzf is where? It's here, right? So what kind of superscalars, what kind of module is this? Remember we talked about RPQ is like an R sub C module. Just the commuting supernumbers. Like if I was to try to, so in other words, if I take y and I multiply it by a tuple, like x theta, I basically get yx and y theta, so to speak, all right? Okay, fine.
It does have to still be one side commuting, one side anti-commuting.
Right, I want it still to be an element of RPQ in order to make that.
So y has to be commuting.
Right, y has to be commuting, otherwise it wouldn't make sense. So I should only consider those kinds of things. And I think, actually, in view of that, it might not matter which side I put the h's on. Anyway, you know what? Let me trust. Let me trust myself here, just for a minute. Just stick with the definition which is written, not try to make new ones. I'm just saying there's a choice that we made there. And anyway, that choice being given, if you look at it, right? Goodness gracious. So I want to say, suppose you have a supernumber, alpha times h, right? Where does that appear? Well, if you, I don't want to write it out, but that appears here, right? Like alpha h m is just equal to alpha times hm for each m. So the component, like what appears there would be just this. But then you can pull the alpha out front. And so what you'd have would be alpha dz f of h, right? But you know what? Alpha's a commuting scalar, so I could also write dz f h of alpha. So I guess, I'm sorry, you know what I'm thinking? There's something clouding my mind. I'm remembering a larger discussion of superlinearity where there's a distinction between right and left linearity. But if we're only dealing with commuting superscalars, I don't think I can tell the difference between right and left linearity. Sorry, there are many flavor choices. Now this, you might recognize this statement right here. I mean, this is the essence of what it means for f to be superdifferentiable, is that you can pull a commuting superscalar out of the argument of the differential. And did you take complex with me?
Nope.
Ah, curses. So in complex, I define basically this. If you have the differential from c to c, what it means for f a function from c to c, guess what? If you assume that f is complex differentiable, what it means at the level of the differential is that if you look at like h times c, you can say you can pull a complex scalar out just the same. That's complex linearity. This is superlinearity. It's just the same. This forces the shape of the matrix of the Jacobian to have a very particular shape. It makes the shape of the matrix look like this. It forces that pattern, and then that's equal to ux, minus uy dx.
Oh yeah.
Vy, and so you get the Cauchy-Riemann equations. Ux equals to Vy, and Vx is equal to minus Uy. I mean, this is the start of complex analysis, but
I think you briefly mentioned that.
It would just be Uy in the matrix, right?
what's that?
It would just be Uy in the matrix. You put minus Uy.
Oh, thank you. Yeah. So
That was like, wasn't that like the condition if something is complex differentiable that has to be the matrix? Like,
right.
yeah.
So
And I forget where I've seen that.
I think I had a homework in advanced on it. I tried to tie the ideas together, but I talk about this in considerable depth when I teach complex, right? It probably won't be as emphasized this year, although I should try to get a certain person to emphasize it. Anyway, my point to you is that superdifferentiability, it's just the same thing. And I think this is a little bit hidden in this definition, but it's there. It's just implicit within this. If you can write such a formula, that means it's superdifferentiable. But if you just want like a simple, to the point algebraic characterization of it, it's that you have, I would sometimes call this lambda zero linearity. See, this RC is the zero of lambda r, right? So you could also say that dzf is lambda zero. Sorry, my notation a little rusty. Lambda zero r linear on RPQ. Now, these g's are exactly the superpartial derivatives. So like, g, so basically your gm f is denoted partial f partial zm, and g alpha f is exactly partial f partial theta alpha. And these definitions will reproduce the patterns I showed you guys in the example the other day. Like, what are properties? What are the properties here?
derivative of some is some derivatives.
Right. So we have, yeah, like ddz, oops, sorry, partial zm of f, plus or minus g is partial f, partial zm, plus or minus partial f, partial zm, that's true. If you have partial zm of a product of f times g, and suppose that f and g are they're both mappings into, say, lambda 0 union lambda 1, so like their output is of definite homogeneity. I mean, probably the only examples I know of, I've never worked with functions that are like partly commuting and partly anti-commuting outputted. Like they're usually just totally commuting outputted or totally anti-commuting output. Anyway, if the parity of f and g is defined in terms of the range, then you also get this graded Leibniz rule, this partial f, partial zm, g, plus minus 1 to the epsilon m, f, partial g, partial zm. And this, you can start to see why it's that rule if you start thinking about all right, so to discover this rule, all you got to do, right, is you got to multiply. So you got what? You got like sum of, let's say, hm g, well, let me just use the notation more to the point, partial f, partial zm, right? That's the linear, so let's see here, how can I say this? How do you discover the usual product rule? One way that you can do it is to multiply the linearizations and sort of like pick off the linear part of them. And so if I have, so this is something like, to go f at the point, let's just use P's bad choice. Let me omit the point there. I'm not going to get in trouble if I omit it. So you have f plus this linearization, right? And then you g plus its linearization. Then you have an error term for g, you have an error term for f. Those things go to 0 in the limit that you're thinking about. And basically you can see that you just pick off the linear piece, and then you can argue that that linear piece is in fact forming the Fauché derivative of the product, and consequently then you can also observe that it's superlinear, lambda 0 superlinear, consequently the product of superdifferentiable functions is once more superdifferentiable. But just getting to the salient feature here, if you multiply this out, you see what happens is you've got a sum over m, and you see what happens is you have hm, right? Partial f, partial zm, g, right? Plus what? I'll just write down the relevant terms. Plus hm, well, there's an f here, right? Because f is on that side. And f is not like the constants I was just talking about. F could be anti-commuting, and some of the h's are anti-commuting as well. So in order to switch those, which I need to do, this costs me a minus 1 to the epsilon m, because, parity of f. And as you can see, I just discovered my mistake, which is that it also depends on the parity of f, right? And so when you do that, you have sum over m, hm times stuff. Well, that stuff is partial zm, g plus minus 1 to the epsilon m, epsilon f, f partial g partial zm. And then there you go. This has to be the so-called GM of the product of f and g. Consequently, there's the partial derivative of a product in terms of product of the partial derivatives of the factors with an appropriate sign added on. And this is how you can prove the graded Leibniz rule, roughly speaking, in the context of superdifferentiable. Now, if you have fresh in your mind, I could easily, if I wanted to go a different way with advanced calculus, what I could do is I could teach the ordinary analysis the first part of the course, and I could say, nobody cares about differential forms. Everyone cares about my thesis. And then we could spend the last half of the semester just redoing everything over super numbers. It would almost be boring because it's so similar, just with some pluses and minuses thrown in. That's why I like this formalism as opposed to the sheaf theoretic formalism, because you guys are actually understanding what I'm saying right now, and I haven't lost you in sheafs and morphisms and other things that I should learn about, because to be a mathematician of the 21st century, you need to learn these things. But anyway, or 22nd century, or I don't know, whatever century you're in. But
Wait, what is a sheaf?
I'll let you guys do your counting. But counting isn't something I'm supposed to be able to do. So
That's not math.
that's not math. Counting.
Wait, what's a sheaf though?
What's a sheaf?
A sheaf, yeah.
Well, I don't know. I mean, I can tell you this much. People who understand what they are say, like, imagine yourself before you knew what a function was. All right?
Mm-hmm.
And then you ask somebody what's a function. Could they explain it to you without defining it? It's like a fundamental notion. It's as fundamental as what a function is. But it's beyond functions. Things that functions let you down for, sheaves pick up on. It's necessary to study higher complex geometry, where points and functions don't quite cut it. Yeah, or maybe another way to look at it would be just you have to go to infinite dimensional points. That seems to be another possibility in my suspicion. I'm just going off a raw analogy. If infinite dimensional sets of points gives you enough room to construct superanalysis, maybe that gives you enough room to do the same things that they're doing with sheaves and such. I don't know. I speak from a position of ignorance, so I should stop speaking. Okay, so what does it mean for a function to be twice superdifferentiable? It means that these functions themselves, the superderivatives, are once superdifferentiable and continuous. Thrice superdifferentiable. You see where we're going with this. Thrice super. So you define higher superdifferentiability in the iterative way as usual, and you can say a function is super smooth if it has arbitrarily many continuous superderivatives. So there's that. And then what's a supermanifold? Well, in brief, a supermanifold is just this. You've got some kind of abstract set out there. I usually say M. And it comes equipped, all right, with an atlas of charts, all right, such that if you pick any particular point and two of those charts cover it, right, maybe you've got psi, and maybe you've got phi, phi, whatever. These give you local homeomorphisms to RPQ. So this would describe a real supermanifold of dimension PQ. It's in local bijection to this superspace. And we insist then that the transition functions, which would be what? These guys. So
basically an atlas on like a supermanifold is basically like the equivalent of a metric to like
it's a set of coordinate charts whose domains like cover the whole thing. So that the supermanifold itself is, you think about it, it's just like an abstract set. I think you could start with a more topological thing. You could suppose it has certain topological conditions, which I can't tell you right off the top of my head at the moment. But you probably need to say some things about Hausdorff or
so an atlas
not too infinite,
Okay.
perhaps.
So basically an atlas doesn't give it shape, but it just gives its coordinates, you're saying?
Yeah, it gives us a way of doing calculus locally on it.
Okay.
Or in this case, supercalculus. Supercalculus being the calculus defined on this space, which I've just started us on. But I gave you the definition of superdifferentiable. You can prove product sum, appropriate quotient rule, chain rule. Proof of the chain rule follows through pretty much the same way you did before. All your favorite basic mechanical operations on supercalculus go through just the same as in the ordinary calculus with some extra signs. Kazul signs, actually. I believe the same Kazul. But this what is this map? I sometimes get it wrong. What is it?
Phi of sine inverse.
Phi composed of psi inverse. Now what is it? This is the transition function on supermanifold. What makes it a supermanifold is that these mappings have to be super smooth. I'll be over there in a minute.
All right.
Yep. These mappings have to be super smooth. It's almost time. Actually got 8 minutes. Well, 7 minutes.
The linear
Yeah.
kid.
Yeah, it's linear. These mappings have to be super. Any place that there's an overlap between two charts, the transition functions on that overlap have to be super smooth, as defined in terms of the lambda zero linearity of the differential. So this in a nutshell is what a supermanifold is. You can talk about supertangent space. And you could look at supertangent space. There's a couple different ways to look at it, but you probably won't be surprised to hear me tell you that partial ZM at a point, x comma theta or whatever particular point, that's going to give you derivations, and we can say that although I don't know if we do that, I may take I forget my thesis. I think I might take the equivalence class view of the tangent space, like its equivalence classes of curves, and then there's some natural tie-in with this. But another viewpoint would be that these are super tangent vectors also, and that you can build any super tangent vector from a linear combination of those guys. So a lot of the things we said about tangent spaces will follow through, but there are some surprises. So anyway, the main thing I was trying to communicate to you guys today is just what is a super differentiable function. I guess I haven't given you an example yet.
I mean, it seems to make sense though, because like you said, it is like mirroring what we were doing before, just in terms of super numbers instead of.
Right. If you get down to the level of Grassmann generators, you can easily write down formulas which won't be super linear. Like if I do something like f of Zm is equal to the body, f of z is equal to the body. I don't want to say this is a notation. So that's a notation for a PQ tuple. Okay. So if I just say it's like the body of, say, I don't know, C1 or something. I don't know. You can make any number of things. I bet that is not. And you could say multiply by a given super number, say alpha, I don't know, whatever.
Mm-hmm.
I bet that will not be, it's going to be Fauché differentiable for sure, because it's a projection onto one component, one Grassmann component, and multiplication by a number. Those things are continuous with respect to the one norm. So it will be Fauché differentiable, I'm pretty sure this will be. And I might even be able to write down the formula for it. But I'm pretty sure this won't be super differentiable, because if I
It's not super linear, is it?
no, I don't. I think if
So if you multiply.
I guess I need to find out what's DFC. What happens if you look at the difference? Anyway, that would be a good exercise, is to show that is Fauché differentiable, but not super differentiable. I'll let you, if you have some time, think about that. If you can figure that out, that probably means that'd actually be a pretty decent exercise to try to dig into it. Okay, so when are we meeting again?
Tuesday, I think.
Tuesday, all right. So we haven't figured out the time yet. Tuesday. Do we have? I'll be over there in a minute. Do you have
I think I've got pretty much all day Tuesday.
all day Tuesday? Okay.
How late are you thinking of going?
Well, I cannot go past 5.
Okay,
So
so
there's
that's
that.
good. That's good.
I'm
Yeah.
pretty much stuck at 5.
I was hoping to head back to Pennsylvania. So.
Yes. But I will try to send you guys a copy of the paper we're going to be trying to understand. Alice Rogers wrote this paper on a particular kind of supermanifold built over a finite number of Grassmann generators that has, she constructs it like as a quotient space, right? I'd like to try to mimic that construction in this infinitely generated context.
So we're going to study that paper and resources you give us, and then come in Tuesday and try to work with it.
Right.
Okay. And then what time do you want us to come in?
That's a good question. So I will email.
Okay. Please don't say 8 a.m.
Probably it won't be 8 a.m. because I don't want to be here at 8 a.m. either, but it probably should be somewhat early because it'll take us a while to unwrap this stuff. But in order to produce a supermanifold, what we gotta do is we gotta find an abstract set, first of all. Then we have to produce a coordinate chart, right? And then I'm hopeful that we might be able to do that. I mean, you can already, if you understand what I've written so far, you can already produce some supermanifolds. They're pretty easy. Like if as soon as somebody defines a manifold for you and they ask you for an example, your immediate reaction should be, there you go. Haha. And the identity map is a global coordinate chart, right? That's also true here. RPQ is itself a supermanifold with the identity map being a global. You could say super chart if you want to
Super.
be snazzy about it.
So that words you can add super on to.
You can add super on just about everything here.
Super complex analysis. Super.
Okay, guys. Anyway, thanks.
So when